let's pick up where we left off. We're going to quick review here. Remember on Friday we were talking about what atoms do to make themselves satisfied as far as, remember the octet rule, trying to get 8 in their outer shell, unless you're talking about hydrogen or helium. So if they need to, they can share electrons, they can donate them, they can accept electrons from somebody else, and really that's going to relate to what we're going to be talking about here with ions. Okay, atoms that carry a charge due to an unequal number of protons and electrons, which is what we were talking about at the very end of last time with sodium, chlorine, potassium, and iodine, which either tried to get rid of an electron or bring one in. Okay. Now you can describe ions as atoms that no longer have number of protons equal to number of electrons. Notice here where I have the equal sign, I've got to strike through it. And so that means they have a charge, because no longer are positive numbers and negative numbers equal. Okay. This transfer of electrons from one atom to another to increase the stability of the valence electron layer to satisfy the octet is called ionization. Okay, 2 examples here. We talked about these the other day. And now we show what's actually taking place are sodium and chlorine. Sodium loses that last electron and thus ends up becoming positively charged. Okay, because originally there were 11 protons, 11 positive charges, 11 negative charges, but now we've lost one of those negatives, so now we have 11 positives and 10 negatives, so now we're +1 for sodium. Okay, so a lot of times you'll see sodium listed off as Na+, okay, which means it has +1 charge. Okay. Chlorine, on the other hand, becomes an anion because it accepts that electron from sodium. And so now chlorine has one more negative than positive. So chlorine, and they changed the name for whatever reason. This is pretty typical. When it becomes negatively charged, they call it chloride. Like iodine becomes iodide, fluorine becomes fluoride. Okay. It's negatively charged. Okay. If it has just one negative charge, it would just say Cl minus. If, and sometimes we do see this, it has 2 negative charges, it might say minus minus or 2 minus. Okay, just like with, magnesium, for example, and calcium, Ca++ becomes, 2 positive charges because it's lost 2 electrons. Okay. Now, what was that cartoon at the front page of our lecture meant to say or meant for us to remember? Told you guys this phrase the other day would come back. Opposites attract. Okay, and I think you guys would all agree with me that sodium with positive charge and chloride with a negative charge are opposites now. So the cation, in this case, sodium, which is positively charged, is attracted to the anion, in this case, chloride, which is negatively charged. And what happens is the formation of an ionic bond. Our first bond to discuss. This is simply the strong electrostatic force binding positively and negatively charged ions together, or cations and anions. Okay. In general, ionic compounds exist as solids with an orderly repeating arrangement of the ions as in a crystal of sodium chloride, which was where all those sodiums and chlorides are kind of just clumped together. What do we best know sodium chloride as? Table salt. Okay. In our body, ionic bonds are found mainly in our teeth and bones. Calcium ionically bonds to certain things and gives really great strength to our bones and teeth. We also have a lot of ions that are floating in our blood and other fluids in the form of electrolytes. Okay, because what happens when you dump salt in water and you stir it up, the salt does what? dissolves. It breaks apart. Those ionic bonds get broken apart. We'll talk about why that is with water here in a bit. And so that is what happens in our body where we have lots and lots of water. Okay. I'm sure you've heard the term electrolytes before. You know, anytime you watch Gatorade commercials, it says great, you know, source of electrolytes. Just a fancy way to describe it. It's got lots of sodium, potassium, chloride, lots of ions in it, essentially. Things that we can lose when we sweat, for example, because our sweat is super salty, which I imagine a lot of you knew already. Okay. Table 2.2 lists off some of the common ions in the body. Some of those we'll get super familiar with. Hydrogen ions, H+, sodium ions, potassium ions we talk a lot about. Calcium, Ca2+, we talk a lot about. Phosphates, we'll talk a lot about phosphates, like an ATP, bicarbonate, so on and so forth. I'm not going to require you to know the table or anything like that, so don't freak out. Okay, so that's the first type of bond, which is fairly strong, but not nearly as strong as our second type of bond. The strongest bonds are covalent bonds, where we share electron pairs. Now, a pair is how many? Two, okay? You can share one pair, which means you share two electrons. We call that a single covalent bond. The example shown here is with hydrogen bonded to hydrogen, okay? Hydrogen in itself, by itself, has that one outer electron. It's not happy until it has how many in its outer ring? Two, okay? Typically it would be 8, but hydrogen's an exception because it only has that one ring, right? Because that one ring can only hold 2. So hydrogen here is not happy, hydrogen here is not happy, but if they lock arms together and they share those electrons, they both end up becoming satisfied for their octet. A double covalent bond, like what happens when we form oxygen gas, is where we share a total of 4. 2 pairs are shared. So look, if we go through and count this one, 1, 2, 3, 4, 5, 6, it's not happy, 6 here. But when we share these, if we count them up, there's 4 here, 5, 6, 7, 8. That one's happy. Same thing, 4, 5, 6, 7, 8. That one's happy. Triple covalent bond, like what we use to form nitrogen gas, which happens to be the majority of what's in the air around us, like 70-something%, 78 or something like that percent of the air around us. Nitrogen gas is where there's 3 pairs or 6 total covalent bonds. Yeah. Now, what's cool about covalent bonds is there are many different ways to form molecules. A simple example would be carbon and 4 hydrogens forming methane, where there's hydrogens on the outside of the center carbon. We'll talk about carbon a lot in our next lecture when we talk about organic compounds like carbohydrates and fats and so on and so forth, where we're going to see all sorts of different chains and rings and double bonds and single bonds and all sorts of cool stuff. Okay. Sound good? Now, one thing to know about sharing these electrons is sometimes atoms are not going to be equal sharers. And here I like to use an analogy that really relates to my personal life right now with a 2-year-old and a 4-year-old and sharing toys. Okay, big brother is a lot stronger than my little 2-year-old. So typically when big brother wants a toy, he just takes it and little brother can't do anything about it. Okay, the same thing can happen with electrons. Okay, so let's talk about when electrons are shared equally. We call those nonpolar covalent bonds. Okay, which means that the electrons will spin equal times around each nucleus. Okay, remember that phrase, opposites attract, right? Within a singular atom, there are opposites. Inside the nucleus are the positive protons, right? Outside in the rings are those electrons, correct? For negatively charged, okay? So there's actually an attraction inside of an atom, okay? And when those electrons are shared, okay, the electrons are going to try to congregate where there's more protons because there's a stronger pull in that direction. Okay. Well, when you have carbon bonded to carbon, for example, in our illustration, there's equal numbers of protons in this carbon on the left to the one on the right, 6 and 6. So they have equal strength in pulling. So the electrons are going to, kind of split down the middle. They have equal custody, if you think of it that way. Down here at the bottom, with a polar covalent bond, the atoms are not going to share the electrons equally. Like with oxygen that has 8 protons, and hydrogen that only has 1 proton. So in other words, this is like 8 times stronger than this one. So where are the electrons going to congregate more towards? The oxygen side. Now, does that mean oxygen's completely taking them away? No, it's like when I tell my 4-year-old to share and he's holding the toy and little brother's just kind of trying to play with it. And says he's sharing, but is he sharing equally? Obviously not. If you grew up with a big sister or a little brother or whatever, you kind of know what I'm talking about. So what ends up happening is we have a covalent bond where electrons are being shared, but we end up creating partially charged regions of a molecule. See these little symbols down here at the bottom? If my little deal will go away. I don't know what this is. But anyway, there's one of these on the other side. There it goes. But it's got a negative symbol next to it. Kind of looks like an S. Okay. You can think of that symbol like it means slightly or partially. Okay. So the oxygen side of our molecule is partially or slightly negative. Over here, that would be slightly or partially positive. Okay. We use the term polar and nonpolar in this class quite a bit. If we want to think of them simply, nonpolar, think no charge. Whereas polar means there is a charge. And this will be stuff that really relates to how we'll talk about cells moving stuff in and out of a cell, for example, relates a lot to polar, nonpolar. So once again, nonpolar, simply kind of think no charge. Polar, there is a partial charge, at least a partial charge. This illustration, kind of like what we saw the other slide a few slides ago, just shows essentially the top 4 parts were the same as what we talked about at the bottom. I don't really know why I still have it in here, other than the bottom image, which is what I want to focus on the most when we form water. H2O is where there's two hydrogens bonded to a central oxygen. And what we just saw is oxygen is stronger than the hydrogens. So look at our figure here, where that ring is kind of being pulled towards the oxygen. What ends up happening are 2 polar covalent bonds, and then oxygen as a result becomes slightly negative and the hydrogens become slightly positive. So we can say water as a molecule is polar. It is partially charged in distinct different regions. Now, why does that have anything, or what's the importance of that? Because that affects our third and final type of bond, what we call hydrogen bonds. I'm going to write or type something up here for us. Hydrogen bonds are an example of what we call an intermolecular bond. An intermolecular bond translates to tell you inter means between, molecular, between molecules, This is a bond between already formed molecules. So this is unique in that if we go back to covalent bonds, ionic bonds, we're forming a bond. We're forming a molecule. We take a hydrogen, we take another hydrogen, we form a molecule of hydrogen gas. We take sodium ion, chloride ion, we bond them together, that's sodium chloride, okay? With hydrogen bonds, what we're doing is we're taking an already formed molecule and we're sticking it to another molecule. Like what happens when you take water, H2O, and you bond it to another water, another H2O. You're not forming a new molecule, you're sticking them together. Okay, and it all relates to opposites attract. Okay, so let's read through. Hydrogen bond forms when a hydrogen atom with a partial positive charge attracts the partial negative charge of neighboring electronegative atoms, most often large oxygen or nitrogen atoms. They result from attraction of oppositely charged parts of molecules rather than from sharing of electrons like covalent bonds or the gain or loss of electrons as in ionic bonds. Okay. If we look at this illustration, each of these things that looks like Mickey Mouse is a water molecule. The big red blob in there is the oxygen, which we just learned is partially negative charged. Each of the little, what is that, gray, is partially positive charged. Notice the dotted lines that are shown here are going from red to gray, or you could say gray to red, from partially positive to partially negative. Opposites attract. Okay. Hydrogen bonds are weak in comparison to ionic and covalent bonds. Okay. But these are hard to break at the same time, which sounds really stupid, but I'll make sense here in just a second. Okay. Think of it like two junior high kids dancing at a dance. Okay, so here's this dumb, I love analogies, but hopefully it makes sense. Okay, so you're 14, you have your first love, you go to your dance, and you're dancing right up on top of each other. Okay, teacher comes over and tells you, okay, separate. What happens as soon as teacher goes away? Separate and you come right back together, right? That's what happens with hydrogen bonds. They're constantly breaking apart, but then just reforming. Breaking apart, reforming. Breaking apart, reforming. Okay? And this is really cool, and it explains something we'll talk about in our next lecture. It gives water molecules and water as a whole very special properties. Like why it's kind of hard and takes a while to boil water. Why water holds heat in the atmosphere and why it becomes humid when there's a lot of moisture in the air. Why water likes to stick to itself. Why things dissolve in water, like salt that we've been talking about. We'll talk more about those things in our next lecture. Okay. Now, we also see hydrogen bonds not just with water, but like DNA. Everybody knows what DNA kind of looks like, right? It's a double helix and it's coiled. The coils, the reason it twists like it does, because of hydrogen bonds. A lot of proteins form fancy shapes because of hydrogen bonds. We call them hydrogen bonds because typically hydrogen's involved, because hydrogen is really weak and doesn't share or doesn't get to share electrons equally with whoever's essentially the bigger brother in that analogy. Okay, so those are the three types of bonds that we will talk about in this class. Let's talk about chemical reactions now. Okay, there's a very important law in the area of chemistry, and that is the law of conservation of matter, which states that chemical reactions cannot destroy, or excuse me, cannot create or destroy matter, meaning that we have 4 hydrogen atoms before a chemical reaction, we better have the same amount after the chemical reaction. We don't have more, we don't have less. We have 2 oxygens after, we better have 2, just like we did before. Okay. What takes place in a chemical reaction is that we're constantly rearranging molecules by breaking the chemical bonds and forming new ones. Okay, like when we form 2 water molecules from originally 2 hydrogen gas and a singular oxygen gas molecule. This is what a chemical reaction looks like as far as when you draw it up in like chemistry. Okay, there's always an arrow in the middle. The arrow points in the direction of where the chemical reaction is going. So it's always pointing to what we call the products, which are the ending materials. Points away from the reactants, which are the starting materials. Okay. A lot of times you'll see chemical reactions just written out like what's here, instead of they'd put a positive sign here, a plus sign in this case, not positive, plus, and then the arrow going this direction towards the water. Okay. Once again, you end up the same amount of stuff, the matter, from what you started with. There's 2 and 2, so there's 4 hydrogens, 1, 2, 3, 4 after, 2 oxygens, 1, 2 after. Okay. If there's not an equal number, you screwed up drawing your chemical reaction somewhere. Now, great thing is in this class, we don't have to worry about doing any of that. This isn't chemistry. Whenever a chemical reaction takes place, energy is very, very involved. Each chemical reaction involves energy changes. And let's define what energy is. The capacity to do work. Okay. 2 principal forms of energy exist, potential and kinetic. Potential is energy stored by matter due to its position. A lot of times people will describe potential energy as energy at rest. We'll think of it like a ball sitting on top of a hill. Has a lot of potential to roll down the hill, right? Okay, a lot of ability to roll down the hill, but if it's sitting on the hill, it's not moving, so it's just all potential at that point. You give that ball a nudge, what happens? It rolls down the hill. It goes from standing still to moving, where we then change from potential to all kinetic. Okay. Kinetic energy is the energy associated with matter and motion. Makes sense? Now, as far as this class goes, we talk a lot about chemical energy, which is a form of potential energy stored in the bonds of compounds and molecules. Where do we get our energy that powers us? What? It's not a trick question, I promise. Food. Okay. Now, if you really wanted to be specific, you could actually trace it all the way back to the sun, which provides energy to plants, which then allows for us to eat the plant or to eat a cow that ate the plant, whatever. But food. Food is like our own gasoline that you put in your car. Okay, we bring in food like glucose and fats. Those molecules are loaded up with potential energy in the form of chemical energy. We can convert that inside of our cells to allow our muscles to contract and move us, for example, which means we go from potential to kinetic. Okay, that's what we're constantly doing. Now, just like I said with matter, with the law of conservation of matter, there's also a law of conservation of energy, which states that energy can be neither created or destroyed. Instead, it's converted from one form to another. Okay. Conversions of energy from one form to another generally releases heat. Heat is a form of kinetic energy. Can't see it, but you can certainly feel it, right? Like if a fire is burning, right, that fire is an example of taking potential energy in the wood, converting it to kinetic energy with heat and light. Okay. We use heat in a great way to give us a body temperature. Okay? For example, a great, easy way to think of this, when we exercise, what happens to our body temperature? It goes up, right? Okay, we get hot, and that's why we start to sweat. Okay, that's because we're doing a lot of energy conversion. We're using that food energy, that potential energy in our food, converting it to kinetic energy. Same thing happens when your car runs. Turn your car on, what happens to the temperature of the engine? It goes up, okay? Cars and us are a lot alike as far as the engine goes of a car. Okay? They do a lot of energy conversions in cars. We're actually super inefficient, meaning a lot of the energy that we have in potential form is not going to go directly to like movement. It's going to go to that heat. Okay, but we don't just dissipate that heat, and we take advantage of that and give ourselves a high body temperature. Okay. We're warm-blooded as a result, which is different from like lizards and snakes, reptiles. They're cold-blooded, right? What is the big deal about that? We'll think about wintertime. You see lizards and snakes in the wintertime? No, what do they have to do? Hibernate. Okay. They have to get their heat from the sun, and if it's not warm outside, their body doesn't really function, so they just shut down for months. We can stay active year-round. Chemical bonds represent stored chemical energy, and chemical reactions occur when new bonds are formed or old bonds are broken between the atoms. We can classify chemical reactions as either those that absorb or release energy. Okay. Exergonic, think exer like exit. Exergonic reactions release more energy, so more energy is able to exit than what's being absorbed, so it releases more than it gains. Okay. Think endergonic like into or enter. Entergonic, if you want to say it that way. Okay. Those reactions absorb more energy than they release. Now, instead of gonic, you might see the term thermic. So like exothermic, exothermic, endothermic, endothermic, same thing. Okay. So you might see it different ways, but it's the same thing, I promise. Now, thinking back to our first lecture, we learned that there were those basic life processes, separate living organisms from non-living things. We said that like differentiation, responsiveness, growth, reproduction. The first one we actually talked about was metabolism. And metabolism is a term that's used to describe all chemical reactions that occur in our body cells. And there are two forms or two phases. We talked about catabolism and anabolism. Okay, we introduced catabolism as kind of a breaking down from bigger to smaller. Complex is simple. Okay, we're going to talk a little bit more in detail about that now. Okay, catabolism are those chemical reactions breaking down complex organic molecules into simpler ones. We call these exergonic, which we just learned means that they release chemical energy stored in organic molecules. In other words, it's breaking covalent bonds like what we see here with our dimer, which means that these two things are bonded together. We break them apart into individual monomers, which means that they're individualized, so they're not together anymore. And in doing so, energy is released. This is what we do in our body with the food that we ingest so that we can use that energy to power things like our muscles when they contract. Okay, because we can see catabolism involves a chemical reaction called hydrolysis. Hydro means water, lysis means to break, where water is actually utilized to break the bonds. But more importantly, what happens is it releases ATP. which we'll talk a lot about here in this class, more so in the next lecture than this one. But that's the fancy way to describe our energy. Opposite of catabolism is anabolism, where we combine simple molecules and monomers to form the body's complex structural and functional units. Like when we take monomer 1, monomer 2, we reverse the reaction this time and we build up to a dimer where they're bonded together. This is how we take amino acids and we make proteins, make our muscles get bigger, okay, which requires energy. And that's because these are endergonic, since they consume more energy than they produce. Requires energy input, usually in the form of ATP. The great thing about these two reactions is they go together. We break down stuff to form ATP so that we can use that ATP to build stuff up, in other words. Instead of a hydrolysis reaction, this is called dehydration synthesis. If you're dehydrated, you're lacking what? Water. Dehydration means to remove water. Synthesis means to build up. So removing smaller subunits to fuse them together. Or water is removed, excuse me, as the smaller subunits are fused together. And I already talked about this, how they go together, but it's described as being a coupled reaction, which is a key feature of our metabolism. How these things go hand in hand. Energy released from an exergonic reaction, like what we see here, going from a complex molecule like glycogen, breaking it down, forming ATP. Heat is released, as we mentioned, anytime a chemical reaction takes place. We form simpler molecules like glucose, but then we can, more importantly, use that ATP to build something up through an anabolic reaction. Final thing here in our chemistry lecture are the 4 classes of chemical reactions. Definition and kind of an easy way to describe what's taking place with some letters. Once again, a chemical reaction involves interactions between atoms and molecules. In turn, involves forming and breaking bonds. First 2 are directly the opposite of one another, and we've already talked about these. Synthesis is where we go from 2 or more small molecules to form a larger one, like A and B individually, small, but together as AB are big. Decomposition is the direct opposite of that, when a large molecule is broken down into a simpler one. On this final page, I've got pictures to kind of illustrate examples of them. In our first box here on the top left, we have synthesis reaction. 2 hydrogen gas molecules, 2 H2s, an oxygen gas molecule, O2. Combine them together, we got 2 water molecules that are bigger than the atoms by themselves or the molecules by themselves. Over on the right shows you decomposition, where we take methane, CH4, we break it down into the singular carbon atom and the 2 hydrogen gas molecules. Okay. Exchange is exactly kind of what it sounds like. 2 different reactants. Remember, reactants are the starting materials. Exchange components and a result form the 2 new products, like AB and CD, end up becoming AD and BC. This takes place like when hydrochloric acid and sodium bicarbonate combine, ultimately forming 2 new products, carbonic acid and sodium chloride. And then reversible reactions are exactly what it sounds like. Means that they can go in one direction and then reverse course and go the opposite direction. AB yields A plus B in certain situations. In another situation, A plus B will yield AB. So we can have decomposition in one direction and turn around and synthesize in the other. This is what we do with ATP. This and triphosphate. That's 3 of these little purple boxes in that form. We use that, we form ADP and PI, but when we form ATP, we reverse the reaction towards the ATP from the ADP and PI. So, pretty cool. Any questions?